This week's topic is color numerical data. What we are interested here is looking at colors in terms of numbers, not in terms of our visual perception. The idea is to make it more scientific, make it more precise, and to take some of the subjectivity away from making color decisions and color evaluations. When we use instruments and computers to measure and analyze colors, the main language that we use is that of numbers. We go from our visual perception, where we use words like red, green, blue, and yellow, convert those into numbers. Numbers are used to describe many types of physical phenomena, some very accurately, some not so precisely. So not only do we, in science, use numbers to describe color, we also use it to describe many physical phenomena. Newton's 3 laws of motion are mathematical laws, and there's mathematical interpretation of them. In physics, physics is really the application of numbers to physical phenomena. There are very many equations that are used. One of the classic equations has to do with motion. Typical problem would be if I throw a ball up in the air at a certain speed, how high does it go? How long does it take to get to that point? What speed is it going when it hits the ground, and how long does it take to do that? All of those values can be determined by a set of equations that governs how motions act in our environment, which includes the force of gravity. Use numbers to describe our colors. The real question is, how well does your numerical description of color you are working with agree with visual observations? We think of, or we use visual observations as our absolute. We're trying to model that visual system with instruments and numbers. And the idea is, how closely can we do that? In a perfect world, our numbers would tell us exactly the same things as our eyes do. Like, for instance, does something match? Or if it doesn't match, how far is it off? And which direction is it off? Those kind of things. When we do our mathematical equations, the result should equal our visual observations. So that means they both should correlate. So they should move both the same way. And the most important thing is they should produce the same ultimate decision. Does the standard and sample match good enough to pass our requirements, or is it not good enough? The trial fails and you have to reformulate or change things so you get it to match better. That's really what we're getting down to in color industry when we're matching colors. Is it good enough to pass? Now, that doesn't necessarily mean that it's a perfect match and they're exactly the same color. They are close enough based on the criteria that we use for our decision. They are within tolerance. We won't be talking about tolerancing in this discussion, but next week that's what we'll be discussing, tolerancing and how these numbers can be used for that, where they work and where they don't. Unfortunately, they certainly aren't perfect in that area. Now, the problem with using numbers and trying to model our visual system of seeing color is that the human color detection system is very sophisticated and very accurate. You remember it uses cone sensors, the optic nerve system, and several portions of the brain. They all work together correctly to produce the color we sense. Sometimes they work correctly and sometimes they don't. If they don't work correctly, then we have a person that doesn't have normal color vision. They have some kind of color vision deficiency, or the common term we use is they're colorblind. But all of those systems have to work correctly for the person to see what we consider normal color vision, or have normal color vision. So remember back from earlier classes, when we detect light with our eyes, there's two types of sensors that we have. One is rods that are used for really detecting the level of light. They allow us to see in a dark room and really have no bearing on our color vision. The other type of sensors are what are important for color vision, and those are the cones. Those are our color sensors, and there's 3 types. And generally we say that there's red, green, and blue color sensors. Let's look at the cones in a little bit more detail. Note that the responses of the 3 types of cones correspond to the additive light primaries. That's the red, green, and blue. Maybe that's why we consider red, green, and blue to be the light primaries, because they correspond with the cones in our eyes. Most of the cones are located in the fovea. The fovea is in our eye and located in the center of vision, so that when you look directly at an object, that image falls directly on the fovea. The high concentrations of cones there gives us our great visual acuity. That is, the ability to see extremely small details. There are approximately 7 million cones in our eye, and there is no way that our instruments can be that accurate. There aren't 7 million detectors in a spectrophotometer. But here's how those signals from our cones are converted into signals to our brains. We start out with red, green, and blue signals from our cones. They go through our retinal interconnections, and somehow, and scientists aren't sure how this happens, those red, green, and blue signals are converted to our opponent type system, or what we consider our opponent type system. We have red and green signals, blue and yellow signals, and white and black signals, or lightness signals. So we transform our red, green, and blue into blue, yellow, red, green, and black, white signals that go to our brain, and our brain interprets those signals to be the colors that we actually perceive. So when we do instrumental color measurement, what we're actually doing is replacing our eye and brain with instrumentation. So the main components that are in our instrument, or part of our instrumental coloring measurement, are the light source that produces the light that falls on our object, a detector that measures the light that falls on our object. So the light source is kind of similar to what we use in visual observation, but instead of our eye, a synthetic or electrical detector is used to replace our eye. Also, there needs to be something to replace our brain, so we use a computer and computer software to do that. And the one last component that many times is left out of this equation is a trained operator. Just because we have a fancy, expensive spectrophotometer with the best computer software available, if the instrument and software is not used correctly, you're not going to get the correct results. So to do that, you need to have a trained operator. That's a very important part of this whole system. If the instrument is not used correctly, or the output from the instrument is not analyzed correctly, the right decisions may not be made. Again, the last component, trained operator, is unfortunately often missing. Companies, especially molders, will buy a spectrophotometer for quality control and think once they have the spectrophotometer, all they have to do is read their samples in and their standard in, and the instrument will do all the work. Unfortunately, color measuring instrumentation is very good at what it does, but it's a tool that is only as good as the operator using it. So it's very important the operator knows how to use it. Really like any other tool. Consider you want to put in a Phillips screw into a piece of wood. The best thing to do is to have the right tool, which is a Phillips screwdriver of the right side, and have an operator person using it that knows how to put the tip of the Phillips screw into the Phillips screw head and turn it so it goes into the wood. You could also, conceivably, use a hammer to do it. You could put the screw on a piece of wood and bang it in with a hammer, and it'll go in the wood, but it certainly isn't doing the best job. Or you could, if you had a flathead screwdriver, you may be able to use it to get the screw in, but again, it's not the best way of doing that particular job. So you have to have the right instrument, and you have to have the right person doing it so that they use the instrument correctly. If either of those is missing, then you could get results that is incorrect. So correct use of the instrument, interpretation of the results are essential for proper color evaluation. Just because you have the instrument doesn't mean it'll do a good job for you if you don't know how to use it. So here's a picture of our instrumental color measurement, kind of a schematic of what goes on in the instrument. See, the light source shines on the sample. This happens to be a sphere type unit. So the light hits our sample, in this case is a blue sample, bounces off the samples collected in one direction there by the sphere, goes through our device, prism in this case, that splits it into individual wavelengths. We have a slit that's controlled by a scanning device that looks at each individual wavelength in the detector. Then we use some computer software to analyze that and massage the data, and it produces directly a spectral curve. And that's a spectral curve for the blue color that we see in the sample there. It shows reflectance at each it shows reflectance at each wavelength through the visual spectrum. So that's how our instrument actually works. There's some requirements for our light source and detector that are used in the instrument. One of them for the requirement for the light source is it really doesn't have to be a standard source. Generally, it's either a tungsten light bulb, basically a projector bulb, or a xenon flash tube, which is used to produce the light. Now, neither one of those is a standard source, and that's not really important. As long as it has output in all the visible wavelengths, that output can be manipulated mathematically to represent any illuminant. The illuminants are really just tables of numbers, so those can be correlated and calibrated with the actual light source so that we can transform them. The detector needs also to have a response in all wavelengths so that it can detect light so it can detect light of all the wavelengths that we can detect light. And also it doesn't have to be like it doesn't have to have the same response as our eyes. The output can be manipulated mathematically to represent the standard observer. Here's a graph that shows the differences between two types of detectors that are used in spectrophotometers, a photomultiplier tube and a silicone photodiode. And you can see that they both have curves that are much different than how our eye perceives color, which is the middle curve there. And both of those curves are different from each other on top of it. But do notice that they both have response in the area that's important from 400 to 700 nanometers. That way, whatever the response is, it can be converted into the CIE standard observer.